everyone. So I'm very happy to be here, and thank you, Shahar, for inviting me. Shahar was the one that really inspired me to go into the world of neuromorphic engineering. When I was a PhD student and I heard about what Shahar is doing in his work as a PhD student and later as a faculty, it really inspired me to get into this field. So thank you for that. And so my name is Elishai, and I'm heading the Neuro and Biomorphic Engineering Lab at the Open University. And today we are the largest group in the Open University working on brain-inspired machines. So Nimrod already a counterpart, honeybees and autonomous vehicles, and maybe just to show you how more efficient biological systems are, and what really lies, underneath the hood in brain-inspired computing is the fact that we don't have the CPU or memory bottleneck. Everything is really distributed. All we have are a bunch of neurons shooting spikes to each other. We don't have central processing units. We don't have address-based memory. Everything is very different when we are working with spiking neural networks. And what we ask in the lab is how can we do something useful with that? If we don't have a CPU, if we don't have a memory chip, if we can't go to a specific register and ask what is stored in one specific memory, if everything is just a bunch of neurons shooting spikes to each other, how do we program it? How do we do something useful with it? So when I was preparing for this presentation, I thought about what would be the best way to approach it. Should I go to the depth of one of our applications, or maybe just show you a review of what we do in the lab? And I decided to give you the review of what we do in the lab because everything is published. All the details, all the technical details are in the academic papers. You can go and read if you are interested. And I want to give you the breadth of what we do in the lab. So if we want to understand what is really the differences between brain and brain-based learning to more conventional way of learning is the fact that when we are working with neuromorphic learning, we're talking about sparse representations. We have learning on the fly, online learning, distributed computing, in-memory computing. It means that the same devices that are storing the memories are the ones who are also doing the processing, and that all of it is done in an analog spike-based communication. And what we do in the lab is focusing on two main areas. The first one is motor cognition, and the second one is visual cognition. And I use the word cognition, and I chose to use it because I think that the intersection between cognition sciences and electrical engineering and neuroscience and computer science is very, very interesting. And I always find it very interesting that, professors are sitting behind their desk and thinking about neuromorphic application, and they think about large, we heard about it today, about large language models and, computer vision. But it seems that they've forgotten the most amazing thing that we can do as biological entities, and it is to move. And we move more efficiently than any other robots that we can program. So I teach algorithmic robotics in the class in the university, and I can tell that in order to find the right way to move and to decide where I want to go and to design my movements, I need to multiply a lot of matrices. But this is not what's going on in the brain. The brain is doing it in a completely different manner. And this is what we do in the lab. We are building robotic systems which are controlled by cognitive systems. We also do visual cognition. I will talk about it in the second part of the talk. But let's start with motor cognition. So this is essentially a project we started out with Intel and Accenture, and we wanted to use neuromorphic and cognitive circuits in order to control motion more accurately. So there is a lot of data in this presentation, so you don't need to really read it and understand the depth of it. But essentially what we want to do is to replicate the way we know our brain is, and the way our brain is controlling motion and controlling movement, and to translate it into spiky neural networks. So I'm skipping the mathematics and everything, despite the fact that it is very interesting, and just want to show you that that in order to do that, we need to find a way to do something useful with these spikes. So we need to take all these spikes and use them in order to encode information in a way that will allow us to decode it afterwards. And this is called the neural engineering framework. I'm not going to do the depth of it, but essentially it's allowing us to use all these spikes in order to represent data. So this is the first example that I want to show you. So essentially we can control the movement of this dot without using a CPU, without using any register-based memory, only based on the spiking dynamics that we have here in the network. So all we have here are a bunch of neurons shooting spikes to each other, and we can use it in order to design motion very precisely, and then we can take it and build a more elaborated models, which are cognitive models. And if we have a robotic arm, this robotic arm is perceiving this dot and it can chase it and be very accurate about it, despite having no CPU, no memory, nothing at all, only spikes that are controlling its movement. And we wanted to take this framework and do something useful with it. By the way, but why would we want to do it? We want to do it because we show that it is much more effective in terms of energy and in terms of performance than using other PID-based controllers where they are implemented on a CPU or a GPU or any other hardware. So we started out working with this Hexapod. This Hexapod, it's a robotic system. It has a lot of many degrees of freedom, and we wanted to use this spiky neural network to allow it to level itself. So as he is moving through difficult terrains, we wanted to help him balance his gait despite this very complicated terrains, and doing it solely with neural networks. You can read about it in the paper itself, but we showed that we can do it very efficiently only with this spiking dynamics. But this is, okay, so we have this robot that can walk and it can balance himself. We wanted to do something useful with it. So in a recent work, we took this system into Alin Hospital. So Alin Hospital is a rehabilitation hospital in Jerusalem. So as Shachar told you, I'm also a neuropsychologist, which is why I have access to all these facilities in hospitals. So essentially, I'm working a lot with disabled people, and we design a robotic system for them. And this robotic system they can use it to eat and to drink and to do all that, to lift something from a higher shelf or to pick something from the ground. But we want them to do it with our robotic systems, where this robot has no CPU, nothing on it, and it's very efficient in terms of energy. And for us, it's a perfect example for the application, because each disabled person is different than the other, and the system needs to learn the nature of the disability of the patient in order to help him. And here we have a system that can do online learning. It can learn the features of the specific patients and help him to navigate to navigate around. And you can see here in the video, we have a robotic arm, and this robotic arm has different positions, and it can navigate through different modes, and it can be used to lift cup on table to drink with it. You can drink with it, you can take it backwards, and you can lift something from a higher shelf. And again, everything that is controlling the system is those spikes you see shooting up there. We want to take it a step forward and see if we can use our spiky neural networks and to build our cognitive systems to control an autonomous vehicle. So we took a LiDAR and we designed a brain-based system that allows us to process those LiDAR readings in order to navigate through different terrains. So we built with spiky networks and models of the basal ganglia and the thalamus. We did it in the computer, in our neuromorphic hardware. We fitted it with LiDAR readings, and we put it here in this vehicle, and we show that we can navigate through a maze, and we can do it pretty efficiently. Again, all the details are in the paper itself, but we even show that it can perform pretty well on a racetrack. Again, no CPU, no memory, just spiky neural networks. And with them, we can navigate through mazes. We can avoid collisions. We can go to specific targets we can do some very heavy lifting, decision-making with this spiky neural networks. So this is a very quick overview of some of the work we've done in the space of motor cognition. I want to thank NeurMorph for already telling you about neuromorphic cameras and event cameras, so I don't need to repeat it again. But essentially, when we are working with event cameras, we have a high, it's the equivalent frame. We don't have really frames in event cameras, but a very high baud rate, fine temporal resolution, high dynamic range, no motion blur. But the key thing is, how do we take all those events and try to maybe use them and to reconstruct images from them? Because essentially, when we are seeing the world as a series of events feeding through our visual system, through the retina, how do we take all those sporadic points and really create the illusion of seeing something real, which has high resolution and such? So how do we reconstruct an image from an event? And this is a very important task, because the neuromorphic cameras, the more didn't tell you this, but I think that it took it for granted. This is by far the most successful application of neuromorphic computing in the history of the field. I mean, if you are thinking about neuromorphic application, what is the killer application? I think people think about event cameras. This is by far the most successful application. So 2 years ago, in the largest conference in cognition sciences, we said that if you want to reconstruct an image from event cameras, let's look at the brain, because the brain is doing it all the time. The brain is taking all those events that are coming in from those ganglion cells that Timur talked about and reconstruct it into something that we perceive as whole with surfaces and everything. And what we did is we redesigned those spiky neural networks, and with them, taking all those different events and use them to reconstruct all surfaces. So essentially what people have been doing up until now is just using convolutional neural networks, conventional CNNs, in order to do this task. Those were very large networks with large parameter space, and it was based on non-spiking architectures. And we look at the brain and reconstruct it such the way that we can do it with a spiking neural network. It was published in CVPR, this work. And essentially, we took a Laplacian's prediction network. Again, all the technical details are in the paper. You are welcome to read it. We converted it into spiking neural networks, fed it into Poissonian integration network. And again, this is only spikes, nothing about, only spikes is what we have in here. We were able to use it to reconstruct an entire image. And then we said, wait a minute. So we use the brain, what we know about cognition, in order to create better engineering, to design better neural networks. Can we do it the opposite way? Can we use engineering in order to understand the brain better? So this is what we've done here in PLUS Computational Biology. You're welcome to read the details. It's one of the most complicated and elaborated work that we've ever done in the lab. But we wanted to build the entire visual system in the computer based on those spiky neural networks. And we build it, and we build this entire framework. We're not going to dive into the details of it, but essentially, this is what we have inside our retina. And what's going on here, you can see those spiky neural networks taking all the different modalities of the data and explain how can we reconstruct all surfaces and perceive images with full color and with in very high resolution. In order to make it more impactful, we said we need to show it happening in biology. We need to show that this is what's happening in the brain. So we did some experiments with macaque monkeys. We really recorded from brain activities. Again, we will not dive into the details of it. It's a hard paper, I know. But essentially, we correlated what we found in the monkeys and showed this is what's happening in our chips. We have spiky neural networks. They are in complete agreement with what we see in the animal model, and we could show that we can take all this data and reconstruct very complicated images with this technology. And more than that, we were able to show for the first time and explain many things that are many things that are only explainable by our work, like several visual illusions. So visual illusions, many of them are based on the fact that what we perceived as a whole and as the true reality that we see in the world, it's basically only what we interpret of it. And this gap explains a lot of how we perceive the world and what happens in reality. And this is the first time that a biologically realistic model, which is based on spiking neural networks, was able to explain a wide variety of visual illusions by also explaining why me and you perceive the world differently. And then we wanted to also be able to learn from the brain to build colorful images, because when we see the world through event cameras, like the picture that Morad showed you, right, with the blue and the red dots, where is the color? I mean, we see the world in a colorful way. Where is this color? And the fact is that retinal inputs gives us cues about the colors, but we don't have, these frames like matrices of RGB cells. We only have cues regarding the colors, and want to show that we can use these cues in order to build the colorful images. So what we see here are the events, and what you see here are the color cues that the retina gives us. So this is the input from the retina. So as I said, we want to take the opposite direction again. We want to use the neuromorphic system in order to understand the cognition. So we use event cameras to emulate what the retina is doing and use a more elaborated spiking neural network to explain how the brain reconstructs the illusion of vision. So this is not published yet. It's already accepted to CogSci 2023. You are welcome to come to Australia, where I will talk about it for 90 minutes. And essentially what we've done is we show that if we'll take those events data and the color cues, we design an entire neural architecture based on adversarial optimization and UNets and CNNs, and a lot of things are going on in this work. But the bottom line is that we can use all this thing in order to reconstruct colorful images very accurately, only from cues from colors and only events. I mean, we can see here very complete surfaces with different modalities that we've tried, and we are able to do it very efficiently. And then we said, wait a minute, we can go back to engineering. Maybe I can go back to Nimrod's work and add some color to his life, right? Some color to these rockets. Because if you look at what Nimrod showed us, when you see the missile going through this terrain, it's fairly easy when the missile is going through white background, right? But if you need to track the missile itself, I'm only speculating here, where's Nimrod? I'm only speculating, but I think that one of the things that if you want to track this patch of moving events through an active field, you need to find a way to track it. But how you will track it if you don't have visual features? And visual features can be very apparent and much more efficient when you have a color image, if you have some color in it. So only by taking this color cues, and again, using neural networks, we show that we can take this cue, for example, for color, and the events that we've got from the event camera, and reconstruct this image of this person, again, very close to the ground truth, as you can see above. So the bottom line is we can go back and forth from cognition to engineering, and for them to inspire each other. And if you would like to learn more, I happen to write an entire book about it. So or you can come to the Open University and learn the course on neuromorphic engineering. It's by CRC Press. You're welcome to check it out. And thank you.